All right. So everyone can see my slides, right?
Yeah, I can see.
All right, cool. So today I'm going to talk about link speed estimation using probe vehicle data. I'm Gabriel Lee. I'm a machine learning scientist in Amazon, and the work I presented is done in Data 61, previously known as MICTA. So this is the agenda of today. I'm going to talk about motivations and contributions first, then the data source and the assumptions we made, and then come about the approaches in detail. Finally, I'll talk about the result and the conclusions. So speed estimation is an important subject for traffic planners and also operators to identify key bottlenecks in traffic network so they can make improvement accordingly. It also benefits road users with increased awareness of traffic conditions and allow better route choices like the Google Map. So we estimate the speed distribution from the GPS data over the traditional loop detector data, mainly because the GPS data has the advantage of low cost, and also it can produce the vehicle trajectory and the space mean travel time. We also use Bayesian inference over the point estimation because Bayesian inference provides a natural framework to incorporate our prior and domain knowledges. It can also modeling the uncertainty of the estimation through higher order property, such as variance. And it can also naturally dealing with data sparsity, which we usually have in traffic data. So the contribution here is Gaussian mixer model with hierarchical Markov chain Monte Carlo sampling. We achieved the cluster cluster speed observations using Gaussian mixer models. The hidden parameters is estimated for the link speed distribution. And this is a generic approach with reduced computational complexity. So the assumption here is GPS samples of road link are drawn from a number of heterogeneous clusters. This is actually from our experimental study. Usually we get data source from different authorities, and each data source is biased by different driving behaviors and vehicle types, such as some of them from taxi drivers and some of them are from truck drivers. So for each cluster, the speed distribution is Gaussian, normal distribution. For all clusters, their Gaussian means follow a log normal distribution. This is also from the literature I listed afterwards. So this is the graph for the Bayesian network we propose. With a prior P, mixture distribution parameters, theta 1, theta 2, until theta n for the means for each component, and also the observations X. So what we try to achieve is to estimate the posterior distribution based on the observations we have. This is a data set. The GPS data is collected from probe vehicles in the state of New South Wales, Australia, to provide the logistic information, which records the time coordinates, road identifiers, vehicle identifiers, speed limit, along with vehicle speed. The number of points we have for weekdays is around 150,000 to 180,000. So for weekend, it's around 1/10 of the data. It's tend to be a little bit sparse. So the speed we focus on is spot mean speed, which is calculated by the adjacent observations, the distance traveled between them and the time elapsed between them. So we divide them, and then we get the spot mean speed. So there are two kinds of outliers we try to remove to make the data more clean. One is side parking. So vehicles pull over and park on the street likely to be recorded as 0 speed observations. So if one vehicle moves only a short distance with a large temporal interval, the second sample can be removed as outliers. So the second type of outlier is traffic delay in sparse data. As we saw on the weekend, on the weekend, there will be the data on each link will be very sparse, but occasional slow speed observations stop at the traffic light will have a heavy weights in the final result. So we only take them into account if the sample size is large. So this is our methodology. Based on our assumptions, the speed distribution follow a Gaussian mixture model. So each component has a weight p, and each component follow a Gaussian distribution with mean theta and variance delta. So the distribution of component mean follows a log normal distribution with mean b and precision w. The distribution of the hyperparameters mean b and precision w, they follow normal and gamma distribution respectively. So the likelihood function we have for Gaussian mixture model, it's illustrated here. It's it's for observation x conditional on the parameter theta. To estimate the weights for each component and mean alongside with b and the precision w with a posterior function. This is the final likelihood function. Because for the delta, the log normal distribution, the distributions of its hyperparameter mean b and the precision w were normal and gamma respectively, so they form a conjugate prior. The marginal distribution of b and w can be deduced analytically. So we use Markov chain Monte Carlo sampling to solve this Bayesian inference. Mainly, there are two reasons. One is the integral in the denominator is unable to evaluate analytically. Another is a cursor dimensionality. Because when the parameter space is large, the data tend to be very sparse in the high dimensional space. So I'll give a general recipe for the MCMC. Basically, we begin the algorithm with some random assigned position for the parameters. Then we propose a jump to the new position in the parameter space. We accept or reject the jump probabilistically using the prior information and the available data. If the jump is accepted, we move to the new position and return to step 1. If the jump is rejected, we stay where we are and return to step 1. So the final result is a set of samples we simulated and we try to estimate the distribution from it. So this is the hierarchical MCMC we propose. We use Metropolis Hastings sampling to sample the parameter theta and p, because no closed form can be derived for the Gaussian mixture model. And for the log normal hyperparameters b and w, it can be approximated using Gibbs sampling because the conditional distribution can be solved by the conjugate prior. So this is the algorithm in detail. So the first step, basically, we initialization of all the parameters. On the second step, we draw the mean b and the precision w for the log normal distribution based on Gibbs sampling. Then we come to the Metropolis sampling part, which we try to draw the weights for each Gaussian mixture model component and mean for each of them based on the results of Gibbs sampling. So the results is all the samples we draw, and if the convergence criteria are met, will stop. So this is the estimation on the synthetic data. So we set up as the prior mean is 40 and standard deviation 20. Then the 36.46 and the 19.32 is our estimation. The mean absolute error is only 0.0025 kilometers per hour. This is for the Gaussian mixture model estimation. Our setup is 20, 30, 50, and our estimation, you can see it's very close. The mean absolute error is 0.008 kilometers per hour. So we pick one real world data, which is a Parramatta Road city bound linked to Sydney CBD. Monday peak hours, 7 to 9 a.m. So this is the link on the graph. So this is our estimations. We choose 10 components for the Gaussian mixer model. This is their estimation, the weights, and the corresponding means. This is the graphical representation of our feeds. On the left, this is for the parameter theta, which is the mean of the Gaussian mixer model, which follow a log normal distribution. On the right, it's a mixer Gaussian distribution for all the link estimations. So conclusion is we propose a Bayesian algorithm for link speed estimation. The Bayesian network of Gaussian mixture model with log normal as prior. We estimate the posterior distribution with GPS observations. We propose a hierarchical MCMC process. We use Gibbs sampling where full conditional distribution can be derived. And we use MH sampling where closed form derivations is not available. And the future works is, we propose the framework. The framework can be used as a in real-time cases as a fast data fusion framework. The estimation we have can be treated as prior knowledge, and we can use the new coming real-time data as the observations to update our prior knowledge. And also, we didn't talk about the optimization of hyperparameters, such as the number of components, which can be optimized using cross-validation grid search or some non-parametric methods. So another important thing can improve our result is the temporal spatial correlation between adjacent links. Their speed, we can use covariant metrics to represent their relationship. So this is our team website. We have done several traffic projects regarding the New South Wales traffic intelligence system, and yeah, all the information is on it. Okay, thank you, everyone.
Well, thank you, Gabriel. If anybody has any questions, please feel free to unmute your mics and ask the questions in voice, or you can also use the chat box to type any questions. Right, I do have a question, Gabriel. Do you mind expanding a little bit about the implications of your research in practice? So how can this be adopted and implemented by transportation agencies to improve their traffic management?
All right. So there are several use cases. Like one, it can be used as a data fusion framework. So basically, we have data from different authorities and different companies. We try to fuse them together and produce a joint distribution for all the data. Because every data is biased by different driving behaviors and the data type. And their noise is different. By using this Bayesian inference, we can produce the clustering of different vehicle type, different driving behaviors, as long as we can we can model the uncertainty of the data by the higher order properties of the distribution.
So this, please continue.
Yeah, and the second user case is just directly produce the travel time estimation from a single data sources, which is very important to for the traffic planning and for the user to use the roads efficiently, like the Google Map.
So do you create these posterior distributions as a function in time of day, for example?
Yeah.
Well, very interesting. Any questions from any of our attendees?
Yeah.
Hello.
Hello. Hey.
This is Zhang. Ali and Gabriel, can you hear me?
Yes.
Yeah, I can hear you.
Great. I just found out my mic was mute. Sorry, and that's a very good presentation from Gabriel. I'm also the co-author of this paper, and just to reflect more about your question, Ali, about what's the implication of this work. And from my point of view, I worked with Gabriel, and for this piece of work, we had two primary practical goals. One is to produce a speed distribution on any road segments instead of just the mean speed, and then this speed distribution would be much more useful for the transport management because we would know what is the travel time reliability. We would know, for example, how we can plan for the 95th percentile of the travel time as an indication for the road travelers and the road performance. So the first goal when we were actually doing the project was to develop the speed and travel time distribution for each road segment. That's why we want to have a distribution instead of just the mean, a points estimator, or just the standard deviation. And the second thing was to, as Gabriel said, to achieve a coherent framework for data fusion. And Bayesian framework would be an ideal candidate for this case. And one of the appealing property of using Gaussian mixture with a normal prior distribution is we can safely assume that because the observations are drawn from sparse and disparate observations, which may well represent different user classes and driving behavior, as Gabriel said. Well, from data fusion point of view, we wanna consolidate the data sets and believe that they are all drawn from the universal population, and we want to estimate the mean and the variance and distribution for the population. So that was the second goal, and to harness data and use the Bayesian framework to estimate the maximum a posterior distribution for the speed.
Thank you. That's very beneficial.
Thank you.
So are you working on data fusion models right now?
Yes. Yeah, go on.
Okay. I was about to ask who Ali is asking. Yeah, you can answer that.
Yeah, Gabriel used to work with us before he recently moved to US and working for Amazon. And one of the key aspects of the team's research work was to research and develop data fusion framework for transport. And this was regarded as a pioneer work for how to do it for road networks. Now we are moving to how to do data fusion for more general transport networks, including the public transport as well. So we believe this work And the methodology we have explored and the pilot we've done would have very valuable impact on the work we are currently doing.
Sounds very interesting.
Yeah, it is a very good work according to from the team's point of view, and we have presented not only to the TRB audience but also to our local Australian and New South Wales audience. And they saw that it's a good way to explore data fusion framework.
Excellent.
And that's all from me. Any other questions? Gabriel?
I think yeah, I think I got a chat message. Oh, what's a probe vehicle? What's a probe vehicle? I think I got a question from Piven.
You can answer.
Yeah, I think probe vehicle basically is a vehicle equipped with a GPS device. They try to record it about the travel time, travel trajectory. So their target is to record the GPS data observations for traffic planning and network optimization.
Thank you very much for that.
All right.